All right, so welcome everyone to today's physics colloquium. It's my pleasure to introduce Prineha Narang. Prineha is a Caltech alum. She got her PhD in applied physics working in Harry Atwater's group. After that, she moved on to a postdoc at Harvard, and then in 2017, she joined the faculty as an assistant professor. Prineha is an extraordinarily broad and prolific computational material scientist. He worked on a dizzying array of topics, including dynamics of quantum materials, computing hardware, and on and on and on. Somehow she's even found time to start a quantum networking company called Zero, for which she's CEO of the founder. So in today's talk, she's going to tell us about some interesting new phenomena resulting from the interplay between light and quantum matter. So please join me in welcoming Prineha.
Awesome. Thank you so much, Jason, for the introduction, for having me here. And hopefully our folks joined online can hear me. This is the very first hybrid talk I've given, so I'm excited about it for various reasons. I'm going to tell you about some of the work we've been doing in phenomena away from equilibrium, thinking about things that are slightly away from equilibrium, and in some cases also very far away from equilibrium. Before I tell you about the science, I want to acknowledge the students and postdocs who've done this work with me. Some of these postdocs have gone on to start their own groups. And I noticed outside the wall of APCOR awardees, and I've been privileged to work with 3 of them listed on this slide. And of course, an array of experimentalists across the world. I hope to expand that list with some of the folks here in the audience today. Oh, right. Is that better?
Yeah.
Awesome. Like many of us, through this pandemic, I've been doing some thinking. And why are we working on what we are working on? And something that resonated with me was a story from Sheldon Glashow, who talks about our overriding challenge in physics and in science through the lens of an alien that visits us. And she or he decides, upon observing 2 people playing a game of chess, that they want to take on 2 tasks, okay? They're 2 distinct tasks. The first task this alien gives himself is to learn the rules of the game, right? So observes these 2 people and says, I want to learn the rules of this game. And the second task is to be a grandmaster. And through this process, through thinking about this story, and I'm paraphrasing here, Glashow convinces us to think about the challenge we face in science through the same lens, thinking about how we can understand the rules of physics, our laws of quantum mechanics in my case. I think about how we can control some of these, think about the control of quantum matter, and how we can actually get to properties that you wouldn't be able to find naturally in these systems. So to go from an amateur chess player, which is where many of us are at, both literally and metaphorically, to something that resembles a grandmaster, so from observer to choreographer. I want you to keep that story in mind as I talk about some of our work here. I'm thinking about both predicting and controlling quantum systems, cases where we understand rules well enough to actually be able to talk about control meaningfully, and some other cases where we are just learning the rules of the game. So my group works across a set of areas. We think about work in quantum electrodynamics, particularly ab initio quantum electrodynamics. It'll become clear in a few slides when I'm telling you about this, but where we can treat the properties of light and matter on the same level of quantization and look for new observables that come from some of these theoretical methods. Of course, implicit in thinking about these quantum systems, in particular in thinking about quantum matter, is to be able to treat those correlations at a good level of theory, an appropriate level of theory. So we develop methods in correlated electronic structure. In particular, we think about the intersection of these methods with some of those approaches in QED. Those will form a bulk of what I'll tell you about here today. Some of the other work we've done is in thinking about open quantum systems, thinking about how we can treat the behavior of the system bath coupling, particularly when there is a backflow of either energy and information from the bath to the system. And there are cases where this becomes important. Some of these are adjacent to the work in ab initio QED that we do. Of course, we hope all of this will be someday useful for realizing an array of quantum technologies. So when I tell people we predict stuff, we predict the behavior of matter, there's always this expectation that somewhere in a couple of seconds, I'm going to have an acronym or one method to rule them all. And this is where I'll tell you a little bit of bad news, perhaps the only set of bad news in my talk. There isn't a single method that gets us all the way from the left of this slide, where we're thinking about methods in quantum chemistry, to things on the right, where we're primarily invoking methods in condensed matter theory, thinking about things at much larger length scales. And there's a simple, intuitive way to think about this disconnect, right? So when we're thinking about systems where we have a finite systems, we have a few atoms, maybe we're interested in knowing what the orbitals look like explicitly, or as chemists talk about, knowing something about the potential energy surface. Those tend to be methods that invoke the finite nature of these systems. There's no notion of periodicity that we would want to invoke there. However, when we think about methods in materials physics, where we think about knowing something about the band structure, understanding the phase diagram, frequently it's helpful for us to invoke periodicity, for us to think about the system as being an extended solid. And then there is this very nice region in between, where maybe we have a defect in a solid. We want to think about it itself acting as, say, an optically addressable spin qubit. And that's where we want to perhaps even combine methods across quantum chemistry and materials physics. This is frequently referred to as the finite extended system divide. If you've seen that before, I think it can also be intuited as essentially being two different languages for describing some of the same problems. And of course, we end up with slightly different observables from these different approaches. So part of the focus in my group has been to actually synthesize across this divide, in particular for us to be able to think about the behavior of quantum matter that is away from equilibrium. And that brings me to the outline of my talk. I'm going to try and tell you about some of the work we're doing in light matter interactions, starting out with systems that look like the finite systems, where approaches in quantum chemistry are of use. I'm going to take that to extend out to systems that are related to cavity control of quantum matter. It'll become obvious why some of the language is similar across those, but also some things that are quite different. From there, I'm going to switch gears and tell you about some of the work in non-equilibrium dynamics, materials that are really driven, say, by an external excitation, by a terahertz source, or your favorite FEL source out there, and how we can describe such systems. And then if I'm lucky and time allows, I'll tell you about some of our very recent work in transport in materials. Okay, so we think about photon-matter interactions. This is a theorist view of the world. There is light on one axis, matter on another, going from analytical to very computationally heavy techniques. And this is where I'm going to make a case for why there's a need for new methods, in particular methods that treat electronic structure and ab initio methods at the same level of quantization as thinking about the photon. Okay, so they're very, very successful methods in quantum optics. I learned some of these here actually in this very building that treat photons at a very appropriate level of theory, but matter frequently becomes a 2, 3, or if you're very ambitious, a 4-level system. And of course, if you're thinking about the correlations in matter, you're thinking about changes introduced in those correlations, either by direct photon matter coupling or going say via a photon mode. Some of these methods fall short in accessing those observables. They're very successful methods in computational photonics, in particular those that invoke a transfer matrix or finite element methods. And the key to those approaches is to be able to write down a well-defined epsilon or chi that, again, captures the response of the material. And this is where you can then parameterize a transfer matrix method. However, in those cases, then you're throwing away some of the quantized nature of light, which is, again, going to be very important for the cases that we're looking at. And then there are very successful methods in electronic structure theory, density functional theory, other mean field methods, GW. I see folks in the audience that have pioneered some of these methods, and of course, couple cluster singles doubles, which in some ways sets the gold standard in quantum chemistry. Frequently, at least in the native implementation of these methods, you don't have the photon there in its quantized form. You typically treat it in a semi-classical way. There's a need for us to introduce new methods that fall in this top right quadrant, and I'm going to tell you about some of the work we and others have done in this field, where you can formally merge electronic structure theory and QED. As originally shown, you can do this in a fully relativistic limit. We will, in our discussion today, take a non-relativistic case. Again, as we think about coupling to quantum matter, the only relativistic effects we're interested in come from the spin-orbit coupling in the materials themselves. And we're going to think about the hierarchy essentially being very similar to electronic structure methods, right? So I can have QED plus Hartree-Fock. If you've taken a physical chemistry course, this is perhaps the simplest way that you treat correlations in matter, right? There are QED plus other mean fields methods, and you can similarly get more and more complex. You can think about QED and time-dependent density functional theory, which will be one of the examples I show here today, and then get to QED and coupled cluster. And as we go up this ladder, this hierarchy to some version of electronic structure heaven, something that of course occurs is computational complexity increases very, very rapidly. So we'll think about cases where one or the other is more appropriate. And this is an area where we've been developing some of these methods. So let me tell you more concretely about an approach to treat QED, electronic structure, same level of quantization, where we also include nuclei, okay? And this is going to be important because nuclei will allow us, the ability to talk about vibrational strong coupling, right? So when we think about vibrational strong coupling, coupling to an individual vibrational mode of say, a molecular system, in our case, could also be an extended system where you talk about then coupling to the phonons. We, of course, need our all-important electrons as well as our phonons. A second reason to have nuclei, and this is something that those of you who've seen calculations that ignore this would realize, that this is a very natural way to include finite temperature into our calculations. And we know the world is not at 0 K, so including finite temperature in a physical manner can frequently be important. So my full physical system is as so on the left. And if I could explicitly solve it, life would be good. I can't. So I'm going to map it onto an effective Kohn-Sham system, which is the system here shown on the right, where I'm going to subsume these interactions into non-interacting electrons, nuclei, and photons. And the key to this one-to-one correspondence, this is a trick you'll see in various forms in electronic structure, will be for me to find a good mean field exchange correlation kernel. And this mean field exchange correlation kernel is important. It also is, in some ways, the Achilles heel of this method, because this is not going to be something that's general across all different methods. This is, of course, not going to be something that allows us to, the various ways of coming up with this mean field exchange correlation kernel. This is a whole kind of cottage industry unto itself, where people think about how to actually benchmark these relative to each other. So we're going to pick a couple of cherry-picked examples here to see that actually this mapping works, as well as our ability to find such vibrational strong coupling. Okay, so one thing, and this is something that I found quite interesting, is that the changes that are introduced by our photon, our cavity here coupling to the material, is not just going to be the ground state. It's very tempting to say that all I'm going to do is couple to the ground state, I'm going to modify it somehow, and life will be good. In fact, it turns out that some of the more profound changes are to higher line states, and the potential energy surfaces that correspond to this photon matter coupling. I need to think about essentially the entire excited state manifold, all the way up to thinking about the Rydberg states here. And this has been done. The simplest way for us to do this would be now to say, okay, I know time-dependent density functional theory is not going to get me all of those correlations exactly right. It'll be a reasonable approximation, but it'll be a cheap way for me to get also that excited state manifold. And now I have two options, right? So in thinking about this time-dependent density functional theory, I can either explicitly evolve in time. As I do that, I'm going to run into some very natural limitations with how long I can go in time. And there's no way of knowing a priori how long I should propagate. But a nice heuristic here would be that if you wanted to get out to many, many picoseconds, life is going to get computationally very difficult very quickly. However, I can go to a frequency domain. I can essentially come up with and formulate an eigenvalue equation here and look at some of these response functions. And now when I do that, my corresponding Descent equations for this response function will be as follows. And I want to draw your attention to two things here. A, that now instead of just a single mean field exchange correlation kernel, I'm going to have two of them. One of them is going to be this very, very well-known Hartree-Fock, the one that essentially represents the approximation associated with my treatment of matter. The other, which is going to be a little harder for me to come up with and require some thinking, is a mean field exchange correlation kernel that's going to correspond to that photon electron coupling. So we can do this, and we can go to a frequency domain approach, and this is now our equation that we're effectively solving. And we, of course, now split up into the matter block and to the electron photon block. And this is something that we can do, again, to look at small finite systems, okay? This is very important. This, as formulated, allows me to think about, say, a few hundred atoms at most that are in this regime of strong coupling to my cavity. And the types of observables I can access are, what are all the potential energy surfaces? What are not just the energy levels, but actually what does the entire surface look like? And what are the modifications? Are there crossings introduced or removed by coupling to this cavity? And of course, changes to those pi star and other highline states. So as we were doing this, a question that explicitly and rightly came up is, well, you're always going to be limited by these exchange correlation kernels, and they're not something that I can easily generalize to any arbitrary system. So can you come up with a way to actually simultaneously overcome that issue, and also maybe find a way to actually have very non-perturbative effects that are included in this, right? So everything I've said so far is, yes, there are changes to the correlations, there are changes to the ground state, to the excited state, but really, I think the exciting stuff happens where you can capture very strongly non-perturbative effects. And towards that, working with one of my students, Nick Rivera, we came up with a way of introducing this notion of photonic quasiparticles, this idea that I could take my system on the left, which has a whole bunch of virtual excitations of my matter and cavity system. It's something that I can't easily explicitly solve. And I'm going to approximate it with the system on the right, where I have a few virtual excitations of this effective system. And essential to the ansatz I write, going from something that is explicit to something that is approximate, is that there are modes of this effective vacuum that are different with and without this light matter coupling, okay? And this can essentially be thought of as, I have some idea, some notion here of photonic quasiparticles. We introduced this. It has since also been adopted by folks working in, for example, Ido Kaminer at Technion, who's thinking about these in a totally different non-perturbative regime of these Cherenkov type effects that you can excite with electron beams interacting with matter at very, very small length scales. Okay, but for now, this is general, and I'm thinking about my cavity and how it interacts with a few level system. So as we were doing this, and something I'm not going to have a chance here to mention, is that this invokes explicitly a variational principle. It will become obvious if you work through it as to why that's necessary. But I'm now in my next slide just going to call it the variational QED method. Okay, it's this line here in blue. And I'm going to contrast it with a system that I can exactly diagonalize, something that I can do exact numerical diagonalization on. And that's going to be a small system, as one might expect, about 50 photon modes, 2, 3, 4 level system, and a handful of excitations. And what I'm going to do, and this is something I can only do in theory, this is going to be incredibly hard to do an experiment. I'm going to go from no coupling to a regime of really deep ultra-strong coupling, okay? So just to calibrate experimentalists in the room, things on the left here, this is a regime where you'd expect some form of weak coupling, some kind of resonator. It's no longer really in that strong coupling regime. Plasmonic type resonators probably fall at this junction here, and then maybe dielectric and other higher Q resonators further on that path. To get all the way out here, perhaps you'd need something like a superconducting system. Okay, and so this is not really where some of the experiments in cavity control of matter are happening at the moment. Though of course we can envision cases where that happens in future. And something you immediately note is that a standard perturbative theory, in regimes of no coupling and some coupling, everything agrees, right? So that's good. That's a nice sanity check. Everything should agree. As you get into regimes of strong coupling, particularly as you get into regimes of deep strong coupling, you realize that a perturbative theory essentially goes in the wrong direction. This is what I would call lovingly a major discrepancy. So you would be tempted if this plot just truncated here to say that these methods more or less agree. There's some slight delta, unless you look at really a very extreme regimes here to realize that the perturbative theory has the wrong functional form, whereas our variational QED method and exact numerical diagonalization continue to agree for some time. Now, this is a real space method, something that was actually pretty powerful for us to think about the spatial dependence of Casimir-Polder, and again, to think about them in this non-perturbative regime. And this is because we have this notion of photonic quasiparticles here introduced. And so I'm, again, not going to have too much of an opportunity to talk about the various predictions we made, including for those regimes of strong coupling that you only realize in superconducting cavities. But I encourage you to take a look at our paper, and if you're an experimentalist, to think about these. So this idea of cavities modifying matter, particularly modifying things associated with Casimir-Polder, got us thinking, well, is there something else that we can do? And can we actually think about, say, changes to a conventional Leonard-Jones potential that people write down, and the various length scales that are associated with it? Again, I see Mark Wise here. Some of these are from his course, Phys 125. And you'll see that actually in this context, particularly thinking about changes to Leonard-Jones potential, brings up a lot of fairly fundamental questions. Okay, so there are a handful of regimes, right? So I can think about modifications of van der Waals. I can think about dipole-induced dipole, and I can also think about actual bonding that is modified by the cavity. So a slightly different regime for this would be for us to think about a handful of these hydrogen molecules. And I can now talk about these intermolecular interactions. I can think of this very, very classic Leonard-Jones potential. So I have three essentially interaction length scales here. Something that scales as 1/R6, something that goes as 1/R3. So there, something down here. By the way, I encourage you not to read into the depth of this potential. That isn't something that we're going to worry about. But we're going to worry about essentially, are there any changes to the functional form of this well-known Leonard-Jones potential that are introduced entirely by coupling to the cavity? And what we immediately see is that there are changes, in fact, not only to R6 and R3, but also to these infinite range terms that need to be captured. For those of you who think about this from a quantum chemistry standpoint, you immediately realize that for me to actually talk about these infinite range terms, I should be invoking not just some mean fields level of theory, but actually thinking of full configuration interaction. And that's, in fact, what we end up doing for such a system. So this is where we keep essentially all of the correlations. And this is where the rotation, the orientation of my set of molecules relative to each other, as well as to the cavity, will become important. For folks who are following on Zoom, I'm just using my hands to talk about orientation relative to the cavity. All right, and that's also something by the perturbation theory now goes a long way, especially if you can go past the lowest order, for us to think about then the angle dependence again in some of these terms. Okay, so we started to actually try and explicitly calculate this, and this is a really out of the press data here. If we can actually think about the cavity as allowing us to move across different phases, this is a nice visual for this is, can I use my cavity to think about various phase transitions in water? Maybe I can think about these being modified by strong coupling of the cavity. And of course, we start with our very, very simple toy model of a few thousand hydrogen molecules. And those of you thinking are like, whoa, wait, didn't you just tell us that you can't do all of these at a level of theory that is needed here, in particular this QED plus coupled cluster? And you're absolutely right. So we cheat a little bit. We do a few of them at that level of theory. We think about fitting various pair potentials beyond that. This is the type of work that, again, you might have seen some of these pair potential ideas from Roberta Carr and from Ming Chen, who we are collaborating with on this particular topic. And there are changes, actually, very importantly, to that infinite range interaction. These, in some ways, break some of the size extensivity that you would not necessarily expect. So we think that the changes introduced by the cavity to not just single molecules, but also regimes of ensembles of molecules are actually quite profound. The take home here is that it goes beyond just allowing us to pump more energy into the system. It might allow us to fundamentally change the dynamics, allow us to actually think about changes to excited states, and in some ways also think about changes to intermolecular interactions at length scales that we don't have easy knobs to change. Okay, so hold that thought, because this is all so far in a regime where I have a perfect cavity. And that's another thing that experimentalists in the audience might say, well, perfect cavity is not really a real thing, Pri, and they'd be absolutely right. So now when we think about dissipation, we think about interactions with the environment, there are two cases I need to think about. A, dissipation that is introduced by the cavity. This is what one might call the crappy cavity regime. And the other, where you actually explicitly have non-Markovian effects, in particular where there is some strong coupling between the system and the bath. And there's some backflow of information, right? Which is frequently referred to as a non-Markovian regime. Okay, so the case where I introduce the cavity dissipation phenomenologically is very, very simple. Okay, this is the simplest thing I can do. I can add some dissipation associated with say, if you're thinking of these as mirrors, not being perfect mirrors, and in a fabric burrow cavity, and that essentially has the result of broadening out any doublet that I expect in strong coupling. This is simple. This is not at all profound, right? This is what you would expect. I have more dissipation. My nice signature goes away. What's harder is for me to think about this actual explicit non-Markovian effect. So when you think about various types of Markovian dynamics, there are various master equations that we invoke. The most common are Redfield and Lindblad. I'm writing here is the Lindblad equation that's derived under the Born-Markov approximation, so the closed evolution, and then each of these corresponding to the various Lindbladian channels. Okay. Now, what's important here is that this method has been applied to various systems, but it is within the Born-Markov approximation. So this master equation doesn't allow me to actually think about that backflow of information. What I really want is a way, it could be master equation based, it could be a slight variation of a master equation base that allows me to talk about backflow of energy or information. Now, a natural question at this point is, how do I think about this non-Markovianity? What's the extent of this? And in fact, that's a field unto itself to be able to describe formally what is and is not non-Markovian and how non-Markovian something is. We can take a nice heuristic here and say that anytime there is any meaningful backflow of energy from the environment back into the system, I'm going to call that non-Markovian. And cavities that are in this regime of strong coupling will naturally fall into that category. Now, at that point, I'm looking at solving this full Nakajima-Zwanzig equation. This is the master equation that would govern the behavior of such non-Markovian dynamics. This is in contrast to the Lindblad equation that I just showed you. If I try and actually explicitly solve this equation, there are a couple of problems I run into. And the most important one is maintaining the positivity of the density matrices here. It so happens that various approaches that have tried to solve this lose the complete positivity of the density matrix, which can allow us then to get slightly unphysical results. And so this is challenging for practical implementation because of that and other reasons. It's not the only approach for us to think about non-Markovian dynamics. In fact, what we've mostly been using and thinking about is this method called ensemble of Lindbladian trajectories. This is where you take individual trajectories that allow you to go beyond Lindblad's equation, but do not require explicitly solving the full Nakajima-Zwanzig equation. This is kind of a workaround from this technique. And this allows us now to access non-Markovian effects. This is work that's been led in my group by Dr. Prineha Narang. She's done an excellent job in actually implementing this method. And something that's exciting about this is that that we can actually talk about simple models. And what I'm showing here is a simple model. This is something you'd recognize again from quantum optics, a simple Jaynes-Cummings model in the regime of strong coupling, on left being on resonance and right being off resonance. In green here is what I would get with so this is now looking at the excited state population. The Markov approximation says, okay, I have something, I start out here and I lose it over time. That's it, there's no revival. What you see in other methods, including our ELT method, which just so happens to actually very nicely overlay exactly within an exact solution of this system. This is why we picked this system. We could solve it exactly as well, benchmark it. You see the revivals that come from this system back coupling. And this is physically, something you can understand. If I have strong coupling to the environment, I'm going to have some revival. I'm going to have some appreciable backflow of information. You can kind of also see that just visually, if I'm starting out here, this revival here is actually a substantial fraction of where I started at, just in that intuitive sense. This approach that we've introduced actually allows us now not only to think about non-Markovian dynamics and classical computers, which we can do relatively straightforwardly, but this also can be explicitly mapped onto a quantum computation platform. So it's a clever combination of dilation and decomposition that we use, and mapping of each of these individual Lindbladian trajectories. One of the challenges there is, of course, for us to think about how to pick the weights for each of these trajectories and how many trajectories. So at the moment, we know we're doing this numerically, and we know we're oversampling. In future, we hope to get around this problem. And we can map these onto small quantum devices, both superconducting and trapped ion. There's, of course, also been interesting work here in imaginary time evolution on some of those quantum devices. So I think there's a natural analog between the classical and the quantum algorithm here. So all of this was towards us thinking about the behavior of cavity and different types of molecule-like systems in regimes of strong coupling. But I promised you we would get not only a little bit away from equilibrium, we got some non-perturbative action going there. We want to get far away from equilibrium. And the first question that you might have is, okay, so what's my physical system? And the class of physical systems I'm going to talk about here are various types of polaritons. I want to clarify, we're coupling via the polariton, but there might be some other order parameter in the system that I'm then exciting via this polariton. So I don't need to be limited to just the type of polariton I'm exciting. It'll become clear in a second why coupling, say, via the lattice is very easy in some cases, and say it allows us to then think about coupling to the magnetic order parameter. Okay, so polaritons come in many flavors. You can think about just the fact that there's a bunch of electrodes. I can cite a collective excitation of plasma polariton. You can do this in graphene, black phosphorus. There are a whole host of materials where this is possible. There's another set of polaritons I can excite called the phonon polaritons, and this is where I need a polar material, something where I can think about this type of polariton not just getting overdamped. These can be in hexagon boron nitride. These can be in various topological insulator systems, and even in some other types of monolayers like the oxides. Okay. Finally, you think about exciton polaritons. You can, by the way, you can for all of these think about condensates and all kinds of things that derive from the fact that these polaritons are very well controlled. Cooper pair polaritons, magnon polaritons, etc. Two examples I'm going to give you, both will go via the lattice. So I'm going to at some point talk about a cavity coupling to a phonon mode. In one case, the simplest case where I just stop there and I use the fact that I've been able to couple via the phonon, and another case where actually I'm using that to then couple to the magnon. And finally, I'm going to extend that out. This is giving you a little bit of a preview for the next few minutes, where I can use that coupling to then say something about, for example, an unconventional superconductor. Okay. All right, so interactions with the lattice, and I was told to make this talk at least a little bit pedagogical, are somewhat simple. They rely on having a polar material where I have a well-defined LOTO split. This frequently is longitudinal and transverse optical phonon modes. These are things that you'd see maybe out near or mid-IR frequency band. These exist in pretty much every polar system that you can think of, and I'm going to relative to the light line, end up with a lower and say some upper polariton branch. Okay, this is well known for various types of polartonic systems. And now if I take a polartonic system that is a monolayer, there are various reasons, by the way, people are excited about monolayers. A, you can make them and control them, but also it represents in some way the extreme of confining, right? That's the least amount of material I can ever have is a single layer of material. So it's natural to think about what happens with a true monolayer. In that case, the split goes away, but I can still use this TO phonon, in fact, to get this well-defined phonon polariton, even though I don't have an LOTO at the gamma point. And I can do this for various kinds of systems. I can think about hexagonal boron nitride and silicon carbide, but I could also equivalently think about this for types of materials that have not yet been observed to have such a polariton. And the one that we wanted to think about, inspired in part by recent synthesis of monolayers, are the oxide perovskites. Okay, so oxide perovskites, the one that particularly has not been on the mind of most people in condensed matter is strontium titanate, STO. It forms frequently a nice substrate material. Lots of things happen with it. People grow stuff on it. People place, say, interesting monolayer superconductors on it and notice a change in TC. It's in some ways a fruit fly of people thinking about various phases in condensed matter. So in our case, we were inspired by this recent report from the group of Harold Wang of a true monolayer of STO being synthesized, and other reports of people using this STO to modify the, say, the behavior of monolayer oxide, monolayer chalcogenides. I'm sorry. So in this case, you expect, okay, well, the system looks very different from hexagonal boron nitride. So hexagonal boron nitride, everything lives in plane. This has been the beauty of some of these van der Waals systems that are encapsulated by hexagonal boron nitride. Very little happens out of plane. So people think, okay, well, maybe that's in some ways special. What we were surprised by is that the oxide perovskites, which don't look at all like hexagonal boron nitride, they have these pyramids sticking out of the plane. They look very messy out of plane, have very similar dispersions to HBN. And I can see that here for three different examples, of course, STO, but also technologically important materials like lithium niobate, which is also known to be nonlinear. So what I can do now that I know something about the phonon polaritons in this system, is to think about squeezing the phonon polariton. And that's going to be a way for me to modify anything that is coupling to this STO. I can also think about twisting some of these monolayer perovskites. In fact, there are recent both theoretical and experimental proposals around, say, twisted visco that might have some interesting behavior. And I can think about various types of interfaces that I can engineer with STO that allow me to use this phonon polariton as a probe of whatever is happening to something that is in contact with it. And this is exciting because in some ways, this is a system you can characterize at nearly room temperature, and you can think about engineering some of these interactions quite easily. So this was my simplest case. I directly excited something via the lattice in my material, and I immediately showed that it has some properties that are of interest. I don't have to stop there. In fact, I can take this idea of an oxide having a well-defined and interesting IR-active phonon even further. And now I can think about some of these cuprate parent compounds. For example, YBCO. It doesn't have to be YBCO, but we're going to think about YBCO because I can very easily write down the phonon modes associated with it. And this is where the cavity is going to couple first to this phonon mode. And now it has an opportunity to couple to the magnons in this system. Those of you who are familiar with parent compounds, in particular YBCO, know that the antiferromagnetic fluctuations in the system are in some ways believed to be responsible, depending on who you ask, for the pairing glue. And this is, again, a way for us to think about controlling it via the cavity, right? So this is something that is intrinsically hard to control, but going via this slightly indirect route of cavity coupling to the lattice, which then couples to magnons, I have a way of introducing control of such a condensate. And in this case, my cavity is not going to be a Fabry-Perot cavity. I'm going to think about various kinds of things that look like this horseshoe here. These are terahertz resonators. I can very easily think about these being patterned, synthesized, tapes of these being made. In fact, folks like Dmitry Basov and Rick Everett are working on some of these experiments. And this idea is, in fact, turns out a little more general than just the system of YBCO that we've shown. You can think about cavity coupling to the phonon and then controlling some other order as actually being more general than this. You can think about controlling other kinds of condensates and order parameters this way. The cavity control of this phonon mode is in some ways equivalent to directly driving this phonon mode. I know that seems counterintuitive because in one case, I have very few photons, there's a cavity coupling to it, and the other, I'm actually almost hitting it with a hammer, but the idea is almost identical, where I'm using the phonon mode, again, as a conduit to control something that inherently might be challenging. In fact, this field, in part enabled by various terahertz sources that folks have been able to create, but also a wide spectrum of excitation sources across all the way from the microwave to XL techniques and various time ranges that are now possible. You can think of this direct drive as a way to creating new states of matter. And whenever I talk about some of these, I think a natural question that comes up is, well, how is this different from some kind of thermal process? Is this just you're heating up the system and it's going through some transition? And it's not. In fact, these are fundamentally both non-equilibrium and non-thermal. So, maybe I can think about this in context of some coordinate and looking at a regime where I'm probing it. Okay, so if this is my either electronic order parameter or lattice displacement coordinate, if I'm probing it, I'm just slightly wobbling around this bottom here. Of course, if I'm using it to switch, I can actually talk about being in states that are not preferred, things that are actually intrinsically away from equilibrium. I can also think of various critical and highly nonlinear phenomena that are mediated by such driving. This is something that is now being quite successfully applied for driving YBCO. This is a field of nonlinear phononics and YBCO, K3C60. There's a whole set of examples where by driving very well-picked modes, folks are able to actually stabilize the condensate above TC. And this has been controversial, but also been exciting because I think this introduces a level of control over quantum matter that was previously not possible. It also brings up questions in theory that are challenging to address. In particular, well, how do we actually get this far away from equilibrium? I think describing some of these superconductors by themselves is hard. Describing them with an external drive is even harder. So those of you who are thinking about entering this field, I encourage you to think about it. What's in part been exciting about these systems is that folks with picking out either a particular mode or similar are able to find types of excitations that were not possible using sources in the past. This includes, for example, the Higgs mode in various superconductors. Now we know this mode was predicted to exist. People have talked about such modes for a long time. That the fact that it should exist and has been unequivocally found, of course, are two different stories. And in fact, something that we've been thinking about is how we can generalize this idea of Higgs modes in superconductors to find other kinds of collective modes that are similar, but perhaps could allow us to characterize unconventional superconductors. Okay, so there are various examples of thinking about the Higgs mode in superconductors, niobium nitride. Others this is a whole field that is really growing based on various terahertz sources that are available. Of course, when we think about unconventional superconductors, now we want to think about the dynamics of a multi-component order parameter. And something that we're going to immediately realize is actually that these collective modes can be a good probe of such systems. All right, so just a quick overview of what these time reversal symmetry breaking superconductors look like. So we have a nice multi-component order parameter, and now, of course, I have a relative phase that breaks time reversal. Okay, and I can now think about either the relative phase or the relative amplitude in thinking about the dynamics of this order parameter, right? There are many materials that are believed to be time reversal symmetry breaking, but not. It's not easy to characterize this. I don't have, I can't hold up the material and say, yep, there it breaks time reversal symmetry, all good. There are actually two very prominent techniques in this field, mu-SR, and of course, this Kerr rotation measurement that has been introduced by the group of Aaron Kapitolnik. And both of those methods are great, but they also have some limitations. So if we can think about a non-equilibrium way of actually characterizing some time reversal symmetry breaking, that would be exciting. And some of these materials, like the more heterostructures, UT2, UPT3, some of these heavy fermion systems, have actually energized a lot of people in this field. So in thinking about this dynamics, the dynamics of this order parameter, you said, okay, well, what would these collective modes look like? And you can open some old helium-3 literature and realize actually that these modes are in many ways morally equivalent to the clapping modes that people have seen in that literature. And you can work through some of the math and say, yes, in principle, these should generically exist in time reversal symmetry broken superconductors. Of course, what is not obvious immediately is whether they'll be well defined. They, of course, must be below our quasi-particle continuum and also need to survive scattering into various normal channels. And something that we established, this is where the kind of microscopic theory we do comes into play. We can actually establish what these modes look like, both the relative phase mode as well as the relative amplitude mode, and show that they don't disappear. Not only do they not disappear, in fact, they could be unequivocal probes of such TRSB. The warm-up here, always got to start with a warm-up exercise before you show the main result, is our conventional case of P plus IP. This is where I'm going to talk about some mixing angle eta, which is going to represent essentially a ratio of the two components here. You can kind of think of it as the number of Cooper pairs that are in one versus the other symmetry. And I can now write down the spectral function as a function of this is this eta. And I can essentially think about cases where you start to see the mode and then cases where it starts to get overdamped. So it's well defined. In fact, turns out that there are a couple of degenerate copying modes for such a chiral P plus IP system, and they generically exist, are well defined, and should be found in systems that are of this type. In this case, I'm showing you what the results look like for a 2D system. We have since generalized it for 3D as well. So P plus IP is interesting, but of course there are other symmetries that are of interest. For example, D plus IG, when I think about D plus ID and think about S plus ID, there are various candidates from that big list I showed you previously that are believed to fall in each of these categories, but not shown to fall in each of these categories. So what we think is that we can of course use these clapping modes in each of these cases. Of course, now here eta has a slightly more profound meaning because I'm not just looking at a simple P plus IP case. I find these clapping modes, they are actually generically coherent. And in fact, these we think could be very easily detected. Whenever I say the words easily detected, the first question is tell me a little more how these would be easily detected. So both the relative phase mode, everything I showed you so far was for relative phase mode, they're equivalent amplitude modes as well. You can think about AC compressibility, you can think about various kinds of microwave absorption measurements, as well as various nonlinear terahertz probes that I've been talking about from some of the existing Higgs mode literature. So we think this is just the beginning. In fact, there are other kinds of collective modes that you could induce, for example, by various proximity effects and also various kinds of surface modes that could be probes of quantum matter that is typically hard to characterize via other techniques. Okay, so as I expected, I did not get a chance to talk about our work in transport, but I'll just conclude with what I did get a chance to talk about. I told you about some of the work that we're doing in cavity control, in particular, both changes to chemical systems and changes to material systems that are introduced by the cavity, things that you wouldn't really easily be able to do other ways. And I told you about some of the work in directly driving some of these quantum materials. This is, of course, not a comprehensive list of what we work on. And for some of you who've perhaps followed some of the work that we've done in various kinds of quantum technologies, I had to include this because I've been seeing all this news coming out of Caltech with various quantum initiatives. We've been thinking about how, from a theory perspective, we could both predict new kinds of solid-state spin qubits, how we can think about optically addressable spin qubits, and also various kinds of multi-qubit studies. If there's something you walk away with from my talk, is that some of the computational work that's happening at the intersection of quantum chemistry, of materials physics, as well as quantum information theory is exciting. There's a lot more that needs to be done in that space. With that, I'll just say that we're very slowly but surely going from observers to choreographers, and I hope that some of the young students and postdocs in the audience are interested in the work away from equilibrium. I'd like to thank funding as well as thank my group again, and thank you all for your attention. Happy to take questions.
All right, so we can take questions either from people on viewing on Zoom.
Should I see if there's something in the chat, or how does this work?
Yeah, so one of the interesting, findings as you go around the body, so to come out of like the molecular, cavity Blair-Ton field was vibrational energy change.
Right.
Which in that case, it's unexpected because these are non-inert bodies. Once you start going to these more complex Blair-Ton solid, do you see new modes of energy transfer, or is the self-interaction already high enough that you don't get much perturbation of it?
You do see new modes, and in fact, some of the kind of changes to the various potential energy surfaces and the fact that new surfaces are introduced is indicative of there being new mechanisms. I think it's harder to disambiguate because unlike picking out a particular vibrational mode in a molecule, now I have a whole host of options. I have both local as well as non-local modes that I could couple to. Yeah. We think that in like the simple case of going via this magnetic Blair-Ton to control YBCO, there was like one mode that allowed us to actually go after that energy transfer. It didn't have to be just that mode, so we could have equivalently done it via a different pathway, and maybe in that case we would see slightly different.
That's very cool. Kind of the second part of my question. I mean, come from the strong laser field. We try to induce but I mean, I guess I apologize. I'm way out of superconductivity. So are you kind of basically in the cavity trying to induce the same things you do with the strong laser field?
Exactly. Right. Yeah. So the idea is that they're essentially two sides of the same coin, even though they look like they're very, very different regimes. But
we blow things up, and yours hopefully we don't.
So that's the intent of using the word non-thermal, that you're not actually heating the system up, but you're actually somehow controllably coupling to it.
Thanks.
One question from the first part of your talk, the body part.
You want me to go back
so
to
you showed us some diagnostics where you were comparing your simulation techniques to some exact diagonalization. But is there some like minimal experimental setup where you can kind of test these ideas and whether they're actually borne out in laboratory setting?
I think a good case of it would be that regime of very strong coupling that you wouldn't necessarily see in the optical domain, but you'd see it in superconducting cavities. And in fact, if there was a way to use some of the superconducting cavities, say from Will Oliver, and we're trying to make this happen. It's just a harder experiment to simultaneously use those, the coupling, as well as some spatial mapping of the system. But yeah, those would be, I think, a really good test of what we're predicting.
Okay, it's now the thanks for you again.